In this video, we will explore the Dynamic Host Configuration Protocol, also known as DHCP. DHCP is a crucial network protocol that automates the allocation of IP addresses and configures network settings for devices. Join us as we delve into how DHCP simplifies network management and ensures seamless connectivity. So, what exactly is DHCP? Dynamic Host Configuration Protocol is a network management protocol. It automates the process of configuring devices on Internet Protocol networks. DHCP automatically assigns Internet Protocol addresses to devices, providing the subnet mask, default gateway and domain name system, or DNS, server information. It eliminates the need for manual network configuration, streamlining the setup process. DHCP uses User Datagram Protocol, or UDP, port 67 for the server and 68 for the client. Let's explore the key components of DHCP. First, there is the DHCP server, a network server. It automatically provides and assigns Internet Protocol addresses, default gateways, and other network parameters to client devices. The DHCP server manages a pool of available Internet Protocol addresses, responds to client requests, and maintains a leased database. Next, we have the DHCP client, which is any network device that requests Internet Protocol configuration from a DHCP server. This includes computers, smartphones, Internet of Things devices, and other network-enabled equipment. The DHCP client sends discovery broadcasts, receives and processes offers, and manages lease renewals. Then there is the DHCP Relay Agent, a network device that forwards DHCP packets between clients and servers when they are on different subnets. DHCP Relay Agents forward DHCP messages across networks, enable centralized DHCP management, and are often implemented on routers. Lastly, there is the Internet Protocol Address Pool, a range of Internet Protocol addresses that the DHCP server can assign to clients. The server tracks which addresses are in use and which are available. The Internet Protocol Address Pool defines the range of available addresses. It can include exclusions for static Internet protocols and is configured with a lease duration. Now let's understand how DHCP operates through a four-step process known as DORA, which is discover, offer, request, and acknowledgement. In the first step, DHCP Discover, the client broadcasts a message to discover available DHCP servers on the network. The destination is 255, 255, 255, 255. In the second step, DHCP Offer, the server responds with an offer. It contains an Internet Protocol address and other configuration parameters. In the third step, DHCP Request, the client broadcasts a request to accept the offered Internet Protocol address and parameters. Finally, in the fourth step, DHCP Acknowledgement, the server acknowledges the request and sends a final confirmation with the lease duration. Now let's examine the format of a DHCP message. The message includes several fields. First, the operation code, which specifies the message type, where 1 is for a request and 2 is for a reply. Then, the transaction identification, a random number used by the client to match responses with requests. Next, the client Internet Protocol address, which is the client's current Internet Protocol address, if known. Following that, your Internet Protocol address, the Internet Protocol address assigned to the client by the server. The server Internet Protocol address, the Internet Protocol address of the next server to use in Bootstrap. Finally, the client hardware address, also known as CH address, the media access control address of the client, used for identification. Let's explore some common DHCP options. First, the subnet mask with the option code 1 specifies the client's subnet mask, which determines the network and host portions of an Internet Protocol address. An example is 255, 255, 255, 0. Next, the router, also known as the default gateway, with the option code 3, provides the Internet Protocol address of the default gateway that the client should use to reach destinations outside of its subnet. An example is 192.168.1.1. Then the domain name server, with the option code 6, lists the Internet Protocol addresses of domain name system servers that the client should use for domain name resolution. An example is 8888 and 8844. Next, the Internet Protocol address lease time, with the option code 51, specifies how long in seconds the client can use the assigned Internet Protocol address before it needs to renew the lease. An example is 86,400 seconds, which is 24 hours. The domain name with the option code 15 specifies the domain name that the client should use for domain name system resolution of host names. An example is example.com. Finally, Network Time Protocol, also known as NTP servers with the option code 42, provides the Internet Protocol addresses of Network Time Protocol servers for time synchronization. An example is 132.163.97.1 and 132.163.97.2. Let's understand the DHCP lease process. After the discover, offer, request, and acknowledgement process, the client receives an Internet Protocol address with a specific lease duration, which is typically 24 hours. At time 1, which is 50% of the lease time elapsed, the client attempts to renew with the specific DHCP server that provided the lease. At time 2, which is 87.5% of the lease time elapsed, if renewal fails, the client broadcasts a request to any DHCP server. At lease expiration, if rebinding fails, the client must stop using the Internet Protocol address and restart the discover, offer, request, and acknowledgement process. Now let's discuss the DHCP Relay Agent. A DHCP Relay Agent is a network device that forwards DHCP messages between DHCP clients and DHCP servers located on different subnets. It is typically implemented on routers or Layer 3 switches. Why use a DHCP Relay Agent? It eliminates the need for DHCP servers on every subnet, centralizes DHCP management, reduces infrastructure costs, and simplifies network administration. How does it work? The client broadcasts a DHCP discover message. The relay agent receives the broadcast and forwards it to the configured DHCP server. The server responds to the relay agent. Finally, the relay agent forwards the response to the client. Finally, let's discuss DHCP best practices and security considerations. Some best practices include proper Internet Protocol address planning, allocating appropriate address ranges for DHCP pools based on network size and growth projections. Lease time optimization, configuring appropriate lease times based on network type, shorter for guest networks, longer for stable corporate networks. DHCP redundancy, implementing multiple DHCP servers for high availability and load balancing to prevent network disruption. Regular monitoring, monitoring DHCP server performance, lease utilization, and address pool depletion to prevent service disruptions. Some security considerations include DHCP snooping, implementing DHCP snooping on switches to prevent rogue DHCP servers from distributing incorrect network information. Media access control address filtering, configuring DHCP servers to only assign Internet Protocol addresses to known media access control addresses in sensitive network segments. Internet Protocol address reservation, reserving specific Internet Protocol addresses for critical devices to ensure consistent addressing and easier management. And DHCP authentication, where supported, implement DHCP authentication to verify the identity of DHCP clients and servers. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.